It's amazing, isn't it? You think about a huge ship out on the ocean, it's like its own little world, and all the systems on board all working together. And if just one thing goes wrong, well, it can really impact the whole vessel. So, today, we're diving deep, no pun intended, into that very idea, the interconnectedness of shipboard systems.
It's truly fascinating.
Yeah,
And in this deep dive, we'll be drawing from all the material you've provided. Our goal is to explain everything in detail about those critical electrical and safety systems found on ships. But we want to do it in a way that's understandable, not overly technical or overwhelming.
think of this as your shortcut to really grasping a pretty complex subject. You've given us a wealth of information to work with. I mean, we've got everything here. Electric propulsion, fire detection, GMDSS, that's the Global Maritime Distress and Safety System. For those not familiar, high voltage systems, tank level sensors, even things like how ships connect to shore power, what's involved in automation, the challenges of harmonics, the importance of batteries, and even navigational lights. We're going for comprehensive here.
And by the end of this deep dive, you should have a much clearer picture of how all these diverse systems work, why they are absolutely essential for the safety and efficiency of the ship, and crucially, how they all connect and interact on a modern vessel.
Let's get right to it. How about we start with how these massive vessels even move in the first place? We've got some great material here on electrical propulsion. Looks like the way ships are powered has evolved quite a bit over time.
Definitely. It has. When you look at conventional marine power plants, you've got a few main types. You have your diesel engines, steam turbine systems, gas turbine setups, even nuclear power in some cases. And then there are various combined arrangements that blend these technologies. The choice really boils down to several factors. The reliability, of course, is paramount at sea. Then there's the space it takes up, how much it weighs, the type of fuel it uses, how much fuel it burns, the cost, how it works with the other systems on board. And then you've got things like how easy it is to maintain, the vibration and noise it produces, how easily it can reverse direction, and even how many crew members are needed to operate it.
Makes sense. It's a lot to consider. And wow, I was surprised to see just how far back the history of electric propulsion goes. That early example from the 1800s really caught my eye.
Yeah, the concept itself has been around for a long time, over 180 years, actually. You have that early electric ferry in Russia back in 1839. It was pretty basic, powered by an electric motor and drawing energy from a battery. A really early proof of concept, you could say. Then, as diesel engines became more reliable in the early 1900s, there was this problem. They weren't reversible. You couldn't just shift them into reverse like you can with some engines today. So for a while, electric power transmission actually became a crucial solution. It allowed the propeller to spin in either direction, regardless of which way the diesel engine was running. Towards the end of the 19th century, there were even some fully battery-powered electric propulsion systems being explored, particularly in Russia and Germany.
Huh. The reversibility of early diesel engines. I never really thought about that. So what led to the next major phase in electric propulsion? Looks like passenger liners played a big part there.
They did. In the 1920s, you had this push for faster transatlantic crossings. And those big passenger liners, they needed massive amounts of power. At the time, turboelectric machinery was the only technology that could reliably meet those extreme demands. So that was the first generation of electric propulsion on a large scale. Steam turbines drove generators, producing electricity, and that powered massive electric motors connected to the propellers, some of them as large as 29 megawatts each.
29 megawatts. Hard to even imagine that kind of power back then. But then in the 1980s, things shifted again.
Right. By then, diesel engines had really matured. They were much more fuel efficient and cost-effective for many applications. And that led to a decline in steam turbine technology and those early electric propulsion systems for a while. But then a key development came along. Variable speed electric drives using AC to DC rectifiers first and then AC to DC converters. These devices basically acted as translators for different types of electrical currents, and that brought electric propulsion back into the game in the 1980s. Initially, it was in specialized ships like research vessels and icebreakers, where precise speed control was critical, but it also started appearing in cruise ships, where quiet operation and flexible power distribution were important. Even the famous SS Queen Elizabeth II underwent a major conversion to electric propulsion in the mid-80s.
So electric propulsion kind of went full circle, and now we're seeing another wave of its popularity.
Absolutely. This modern resurgence is being driven by the need for better fuel efficiency and much lower emissions, of course. Electric propulsion is now the preferred solution for new ships in various segments, including large container ships and dry cargo carriers. In fact, some estimates projected that by 2020, something like 20% of all new vessels would be using electric propulsion.
Okay, so we know why it's becoming popular, but what are the main types of electric propulsion that are being used today?
So there are several. You have the diesel electric machinery system, which is pretty straightforward. Diesel engines drive generators. Those generators provide the electricity, and that powers electric motors to turn the propellers. A big advantage is that it allows those diesel engines to run at their most efficient point, meaning they burn less fuel and produce fewer emissions.
That makes sense in terms of efficiency. What other types are common?
Then you have coated, which stands for combined diesel electric and diesel mechanical machinery. This is kind of a hybrid system, offering some flexibility depending on how the ship's being operated. There's also dual-fuel electric propulsion, which is interesting because it addresses those non-NOx and SOx emissions regulations. It allows the use of cleaner fuels, like LNG. A good example mentioned in the documents is the LNG carrier built by Mitsubishi Heavy Industries for MISC Berhad. These dual-fuel systems can save a lot of fuel in that specific case, around 20% compared to a steam turbine system. You also have things like Codelag, which is combined diesel-electric and gas machinery, and Cotoidis for combined cycle gas and steam turbine electric. Each type has its own applications and benefits depending on the specific needs of the ship and its operation.
Sounds like engineers have a lot of options to customize the propulsion system for the ship. Now, what are the basic building blocks of these electric propulsion systems? What are the core components that make it all work?
The documents highlight several key components. You have your prime mover. It's usually a diesel engine, but it could also be a gas turbine or, in some specialized cases, even a steam turbine. Then you have your electrical generators. These are the things that convert that mechanical energy from the prime mover into electricity. And then, of course, you need a way to distribute all that electricity, so you have your electrical distribution systems, switchboards, transformers, all that. And finally, you have the propulsion motors themselves. These are what actually convert that electricity back into mechanical power, turning the ship's propellers. And in many modern systems, there are sophisticated propulsion converters, which are like the brains of the operation, controlling the power flow to the motors, so you have very precise control of speed and torque.
So it's all about converting energy back and forth in the most efficient way possible. Now, what are the main benefits of using electric propulsion? Why are ship owners choosing this option?
Well, there are some really good reasons. First, it can really free up space. You can actually reduce the space needed for the machinery by as much as 30% compared to a traditional system. Think about it. Less space for machinery means more space for cargo or passengers, which means more money for the ship owner. Then there's something called load diversity. With a centralized power plant, you can supply electricity for both propulsion and everything else, lighting, air conditioning, all the auxiliary systems. That means you can run fewer engines and optimize fuel consumption. And speaking of fuel savings, electric propulsion can really make a difference there, especially for ships that spend a lot of time at low speeds, like maneuvering in port or just waiting around. You can see savings of 15–25% compared to a mechanical system. There's a great example in your materials, the Norwegian Epic cruise ship. They saw a reduction of around 14,000 tons of fuel per year. Over the life of the ship, these fuel savings can actually more than make up for the higher initial cost of the electric propulsion system. Of course, burning less fuel is good for the environment too.
Wow, that's impressive. 14,000 tons of fuel. So the economic and environmental arguments are pretty compelling. Are there other benefits that come with electric propulsion?
Definitely. Maneuverability is a big one, especially with podded propulsion. That's where the electric motor and the propeller are housed in a pod that can rotate 360 degrees. That means you can turn much more tightly and even move sideways at low speeds. Great for icebreakers, ferries, tugboats, research vessels, anything that needs to be nimble. Plus, the speed of the engine and the propeller can be controlled independently, which gives you more flexibility. And because there are no direct mechanical connections, electric motors are much quieter and produce less vibration. That's a big plus for warships that need to be stealthy, research vessels that need quiet conditions for their instruments, and, of course, cruise ships where passenger comfort is key. Then there's the automation. Electric propulsion systems can have advanced self-monitoring and diagnostic capabilities. Less manual intervention, smaller crews, it all adds up to lower operating costs. And because they can operate efficiently even at partial loads, you save even more fuel compared to traditional mechanical systems. So yeah, the benefits are pretty significant.
You've definitely made a strong case for electric propulsion, but I'm sure there are some downsides too, right? Nothing's perfect. What are the disadvantages of going electric?
There are trade-offs. One thing is that if a ship is constantly running at its top speed, a direct mechanical drive might be slightly more efficient. With electric propulsion, you have these energy losses at each stage of the power conversion, from the prime mover to the generator through the distribution system, and finally to the motors. And the documents go into detail about those potential losses. But, and this is important, technology is constantly improving. They're developing more efficient prime movers, superconducting generators, and motors that reduce those electrical losses, DC distribution systems, advanced power converters, all working to close that efficiency gap. The other big thing is the initial cost. Electric propulsion can be more expensive to install than a traditional mechanical system. And because it's more complex and involves more automation, you need specialized crew training, so it's a balancing act, weighing the long-term benefits against those initial costs.
It makes sense. And what about those podded propulsion systems you mentioned earlier? Can you tell us more about those?
Sure, pod propulsion is really innovative. Basically, you take the motor and stick it in a sealed pod, and that pod is mounted directly to the hull and connected to the propeller. The really cool part is that this pod can rotate a full 360 degrees, which means you don't need a rudder. ABB and Rolls-Royce are the two big players in this market. ABB makes the Azipod, which comes in a wide range of sizes. They have bigger ones above 5 megawatts and go up to really powerful units around 30 megawatts. And they also have a compact version, the compact Azipod, for smaller vessels. Rolls-Royce makes the Mermaid Pod, which has a similar power range. Interestingly, ABB develops and builds their Azipods entirely in-house, while Rolls-Royce works with another company, Convert Team, now part of GE, for the electrical components of their Mermaid Pods.
I read about those electric ferries, too. That was really interesting, especially the one operating in Norway.
The Amber, right. That's a great example of how far electric propulsion has come. It's the world's first all-electric car ferry, running entirely on batteries. It's 80 meters long, made of lightweight aluminum, and powered by two 450-kilowatt electric motors. The batteries are huge and can be recharged super quickly using those shore-based charging stations. And the impact on the environment? Well, it's night and day compared to a diesel ferry on the same route. They've seen massive reductions in CO2 and NOx emissions. And because electricity is cheaper than diesel, they're saving a lot of money on fuel too. It just shows that fully electric ships are becoming a reality, not just a futuristic concept.
It's really amazing to see how fast this technology is developing. What about the advantages of a fully electric system versus a hybrid one?
Well, with a purely electric system, you eliminate all those local emissions while you're running on battery power. No NOx, no SOx, no CO2. Plus, it's incredibly quiet and smooth, no exhaust fumes. And it's not just about ferries. Studies suggest that if you scale up electric propulsion to other suitable types of ships, you could potentially cut CO2 emissions from shipping by 50–70%. That's a huge impact.
Okay, so electric propulsion is definitely on the rise. Let's switch gears now and talk about high voltage electrical systems on board. Now, I know you said that in the marine world, anything above 1,000 volts is considered high voltage. Right?
That's the general rule of thumb. Anything at or below 1,000 volts, it's either low voltage, LV, or medium voltage, MV, depending on the specific context. When you go above 1,000 volt AC, that's when you're dealing with high voltage, or HEV.
And what are the common voltages you typically see on ships?
6.6 kilovolts or 6,600 volts is pretty common for a lot of vessels. If the power demands are a bit lower, you might see 3.3 kilovolts used. But for those really big cruise liners, the ones with lots of power-hungry systems, or even some specialized offshore vessels, they might use 11,000 volts, 11 kiloV.
So why are they going with these higher voltages? The demand for more power, right?
Exactly. Modern ships just need a lot of power, and they keep getting bigger and needing even more power. Think about those massive container ships, especially the ones that have tons of refrigerated containers. They suck up a lot of electricity. Gas carriers that need to keep their cargo super cold, same story. And then, of course, there's the growing use of electric propulsion, which we talked about. All that needs a lot of electrical power.
And I remember that basic power equation from physics: power equals voltage times current. So higher voltage means lower current for the same power, right?
Exactly. That's the key advantage. If you boost the voltage, you can lower the current. And that has a domino effect. Lower currents mean you can use smaller, lighter cables, smaller transformers, and switchgear. Less weight, less space. Plus, it means smaller, more efficient protective devices. It's all about optimization.
So smaller equipment, more efficiency makes sense. But are there any drawbacks?
Of course, there are always trade-offs. Higher voltages mean you need more insulation for all the equipment. That insulation needs to be thicker and stronger to handle that electrical stress, and it can be more expensive. And importantly, there's a much higher risk factor. Working with high voltage is serious business. You need very strict safety procedures and specialized training for anyone who's going near it. One mistake with high voltage and things can get very dangerous very quickly.
Safety first. So what kinds of equipment are we talking about here? What does a high voltage system on a ship look like?
Well, you have your HV generators. Those are the big boys producing the power. Then you have HV switchgear, circuit breakers, contactors, relays, and all that. And all that is usually housed in a big HV switchboard. Then, of course, you need transformers to step the voltage up or down depending on what you're doing. And in ships with electric propulsion, you'll have those high-voltage propulsion motors. Pod propulsion systems like the Azipod and Mermaid, they use HV motors too. And even something like a bow thruster might be high voltage if it needs a lot of power. And then you have all those specialized cables carrying that high voltage all over the ship. And these HV generators, they're typically big, powerful machines producing a lot of electricity. You're looking at power ratings anywhere from 800 kVA to 3000 kVA or more, and generating voltages like 3,300 volts, 6,600 volts, or even 11,000 volts. And they have to be really reliable because the ship depends on them.
I noticed the documents mention brushless generators. What's so special about that design, especially in a marine environment?
Good catch. That's an important feature for reliability. In older generators, you had brushes to conduct electricity to the moving parts. But those brushes wear down and create dust, and they need constant maintenance, which means taking the generator offline. And out at sea, you really don't want that downtime. So now they use brushless excitation systems. It's a bit technical, but essentially they use rotating magnets and electronics to do the job without physical contact. Less maintenance, more reliability, fewer potential problems with sparking and electrical noise.
So basically, they're designed to just keep running smoothly with less fuss. What about the standards they have to meet? These are pretty high-stakes pieces of equipment.
Oh yeah, they have to be built to very strict standards. You've got international ones like the IEC and NEMA, and then you have the classification societies, ABS, BV, DNV, Lloyd's Register, those guys. They all have their own requirements for designing, building, testing, and installing HV generators on ships. It's all about ensuring they can handle the tough marine environment and operate safely and reliably. You don't want any surprises out at sea.
And I'm assuming energy efficiency is a top priority. How are they designed to maximize that?
You bet it is. It all boils down to reducing energy losses. Every little bit you can save translates into less fuel burned and lower operating costs. Designers focus on using top-quality materials with low electrical resistance, optimizing the magnetic circuits in the rotor and stator to minimize those magnetic losses, using advanced insulation to prevent energy leaking out, and making sure the cooling system is super efficient so it doesn't waste energy. Every little bit counts.
Cooling those things must be a challenge, especially with how much power they generate. How do they manage that on board a ship?
It's all about getting the heat away from those components without wasting too much energy in the process. They have two main approaches. In some cases, you can use open-air cooling, where the generator basically sucks in ambient air, uses it to cool things down, and then spits out the hot air. But on a lot of ships, especially in those enclosed engine rooms, you'll see closed-air systems. These typically use air-to-air or air-to-water heat exchangers. The idea is to circulate the air inside the generator and use either ambient air or seawater to cool it down without mixing the air inside with the air outside. It all depends on the generator size, where it is on the ship, and how the engine room's designed.
Okay, so we've talked about the generators. What about those high-voltage transformers? What do they do?
Transformers have several jobs. One is to isolate different parts of the electrical system from each other. That's really important for safety. It stops a fault in one part of the system from spreading to other parts. And of course, transformers are what you use to change the voltage. You might need to step it down to a lower voltage for some machinery, or step it up to a higher voltage for transmitting power over longer distances within the ship. Less current means less energy lost as heat. And sometimes they even use transformers to shift the phase of the electrical supply, which can be useful for reducing those harmonic currents, especially when you're dealing with the variable speed drives used for electric propulsion. It's all about making sure the power is delivered efficiently and safely to where it needs to go.
It's like a complex electrical highway system with on and off ramps and traffic management systems. Now, I saw something about cast resin and dry type transformers. What's the difference between those two?
The main difference is how the windings are insulated and kept cool. Cast resin transformers have their windings completely encased in epoxy resin, which is a tough insulating material that's good at dissipating heat. They can handle a lot of power and voltage, and they're often used in places where the environment is pretty rough. Dry-type transformers, as the name suggests, don't use any liquid coolants or insulation. They use air as the main cooling and insulating medium. That makes them more environmentally friendly because there's no risk of oil leaks. They're also inherently safer because there's no flammable oil involved. And as a bonus, they usually need less maintenance.
And what about materials? Are there specific ones they use for these high voltage transformers?
Oh, absolutely. Material selection is super important here. For the high voltage windings, they usually use high purity copper wire, sometimes round, sometimes rectangular, and it's heavily insulated, of course, to prevent those high voltages from leaking out. They'll also use things like glass fiber webbing or special glass mats impregnated with epoxy resin to provide more insulation and support between the layers of the windings. And the core of the transformer, the part that guides the magnetic field that's typically made of laminated silicon steel, all carefully stacked to minimize those energy losses that come from eddy currents and hysteresis.
We talked a bit about podded propulsion systems earlier with those Azipods and mermaid pods. Is there anything special about the high voltage aspects of those motors being out there in the water like that?
Definitely. The motors in those pods have to be able to operate at high voltage, usually the same high voltage used for the ship's main distribution system. That allows them to draw less current for the same power, which is good because it reduces the size of the cables they need and the energy they lose as heat. They're also specially designed to be super robust. They're out there on the hull exposed to the elements. And of course, they're almost always synchronous AC motors, meaning they need those frequency converters to control their speed precisely.
What about other high voltage motors? What other jobs do they have on a ship?
High voltage motors are used for any application that needs a lot of power. Think big pumps for moving things like ballast water, cooling water, firefighting water, large air compressors for all sorts of ship services. Sometimes even those bow thrusters are powered by high voltage motors if they need a lot of oomph to maneuver the ship. And the types of motors they use are usually either synchronous motors or asynchronous motors. Synchronous motors, those are good for really demanding jobs, like propulsion, because their speed is directly linked to the frequency of the AC power supply. They're very precise, but usually need those frequency converters. Asynchronous motors, on the other hand, are more commonly used for those auxiliary systems. They're simpler and tougher, and they can run at a constant speed right off the high voltage supply. Or you can use a frequency converter if you need variable speed control. And there's a newer type gaining popularity, brushless excitation synchronous motors, or BLSMs. They're very efficient and low maintenance, so we're seeing them used more and more in those advanced electric propulsion systems.
I was reading the section about high voltage safety, and it was pretty intense. What are the main risks you have to worry about when working with these systems?
Yeah, high voltage is no joke. One big thing is the stored electrical charge. Even when you switch off the power, high voltage cables and equipment can hold a dangerous charge, like a loaded gun. That's why earthing or grounding those components is absolutely essential. If you touch a conductor with that stored charge before it's properly grounded, you're in for a nasty shock, maybe even worse. And it's not just about that static charge. Those big inductors, like the ones in motor windings and transformers, they can store a lot of energy too. If that energy is released uncontrollably, it can be really dangerous. And then you have the risk of arcing and sparks. Higher voltages mean a higher risk of that electrical breakdown, which can lead to equipment failure, fires, and injuries. It's a constant awareness thing. Moisture, dirt, loose connections, those can all increase the risk of arcing. You always have to be super careful when working around high voltage systems.
It sounds like you really have to respect the power of these systems, even when they're switched off.
Exactly. The danger doesn't just disappear when you flip a switch. It's about understanding those hidden dangers and taking the right precautions every time. You need to de-energize the circuits, then verify that they're actually dead, and then properly earth them to bleed off any residual charge. It's not something to be taken lightly.
You mentioned creepage and clearance in the context of high voltage.
Yeah.
What do those refer to?
So clearance is all about having enough distance between conductors so that electricity can't jump across the gap. Think of it as a safety buffer. Creepage, on the other hand, is about the distance along a surface. That's important because dirt, moisture, and other contaminants can build up on surfaces and create a path for electricity to leak. You want that creepage distance to be long enough to prevent that tracking. It's all about preventing those high voltages from finding an unintended path and causing problems.
And what about those high voltage cables? What are they like?
You're talking about specialized cables designed to handle those high voltages. They have multiple layers of insulation, carefully chosen to prevent any leaks. They often have shielding layers too, to protect against electromagnetic interference and to contain those high currents in case of a fault. It's all about keeping that power where it belongs, safely inside the conductor.
I came across the terms working in live zone and dead working in the documents. Can you explain those?
Sure. Working in live zone is basically Any situation where you're near high-voltage equipment that's actually energized. It's high-risk, high-stakes work. You need specialized training, specific tools rated for high voltage, appropriate protective gear, and usually a buddy system with a safety observer to make sure everything's done by the book. Dead working, on the other hand, that's when you're working on equipment that's completely de-energized. But even then, you don't just assume it's safe. There are rigorous procedures to follow permits to work, testing the circuits multiple times to make sure there's no voltage present, and then physically grounding the conductors to ensure they stay that way. It's all about eliminating any chance of those high voltages coming back to life while you're working.
Earthing seems like a recurring theme when it comes to safety.
It's absolutely fundamental. Everything is about getting those high voltages safely to ground if something goes wrong. And it's not just about the procedures. They actually build those safety measures right into the equipment. Those high voltage switchboards have all sorts of interlocks, mechanical and electrical, to prevent accidents. For example, if you want to ground a circuit, you have to physically open the circuit breaker first. You can't close the grounding switch if the breaker is still closed. And you can't close the breaker if the grounding switch is closed. Those interlocks are designed to stop anyone from accidentally energizing something that's supposed to be grounded, or grounding something that's supposed to be live. And using calibrated high-voltage testers to double-check everything before you even think about touching those grounding leads, well, that's just common sense when you're dealing with this much power.
It really emphasizes how crucial it is to follow those safety protocols every single time. No cutting corners with high voltage. Let's change gears now and talk about another vital safety system: fire detection and alarm systems. Hopefully you never need them, but they need to be there and they need to work.
Absolutely. It's about detecting those early signs of a fire and raising the alarm as quickly as possible. They use a variety of detectors, each sensitive to different things. You have some that detect smoke, some that sense heat, and some that react to the radiation from flames. Some work by seeing how much light is blocked by smoke. Others measure changes in electrical current caused by smoke particles. And you even have flame detectors that respond to the infrared or ultraviolet light emitted by flames. And sprinkler systems. They often have their own alarms built in, but the document doesn't go into the details of those here. You also have other specialized types, like those line heat detectors they use along cable trays, where a fire might spread.
It's like they've got a detector for every possible scenario.
Yeah.
What about the system as a whole? What are some of the key features?
Modern fire detection and alarm systems are very advanced. They're designed to be expandable, so you can add more detectors and alarms as needed, depending on the size and layout of the ship. They often have voice alerts that can be broadcast over the ship's PA system. And they're integrated with other safety systems like fire suppression, ventilation control, and emergency shutdown systems. That means a coordinated response if a fire is detected. And crucially, these systems have to work reliably even in those hazardous areas, like engine rooms and cargo holds, where there might be flammable vapors or other dangers. They use special intrinsically safe detectors in those areas to prevent sparks.
So you have all these different types of detectors. What triggers them to actually send an alarm?
They call those initiating devices.
Mm-hmm.
Smoke detectors, heat detectors, flame detectors, those are the automatic ones. And then you have manual call points or fire boxes that someone can activate if they see a fire.
Let's talk about smoke detectors for a minute. You mentioned there are 3 main types. Can you break those down for us?
Sure. You've got your light obscuration type, which basically shines a light through the air and measures how much of that light is blocked by smoke. The light scatter type is similar, but it looks for how much light is scattered by those smoke particles. And then there's the ionization type, which is pretty clever. It uses a tiny bit of radioactive material, a Americium-241, to ionize the air inside a chamber. That creates a small electrical current. When smoke gets in there, it disrupts that current, and that's what triggers the alarm. It's very sensitive and reliable, even for tiny amounts of smoke.
Americium-241. That sounds a bit scary.
It is radioactive, but the amount they use is so tiny that it's considered perfectly safe. The benefits in terms of fire detection far outweigh any theoretical risks.
So that's how they detect the smoke. What about the other automatic fire detectors? What makes them go off?
Heat detectors, as you might guess, react to heat. Some of them are set to trigger at a specific temperature, while others detect a rapid increase in temperature, which is often a sign of a fire. Flame detectors are even more specialized. They look for the specific kind of light that flames give off, usually in the infrared or ultraviolet range. And those sprinkler systems, the ones that actually spray water to put out the fire, they have flow switches that trigger an alarm when water starts flowing through the pipes. That lets you know that a sprinkler head has been activated, which means there's definitely a fire somewhere.
It's amazing how much technology is packed into these systems. And then you have those manual fire alarms. I guess they're there as a backup.
Yeah, those manual call points, or fireboxes as they're sometimes called, those are important too. They're usually placed along escape routes, in corridors, and near exits, so anyone who sees a fire can quickly raise the alarm. And they come in different types. Some have levers you pull, some have glass you break, some have covers you lift, but they all do the same thing. They close an electrical circuit that sends a signal to the main fire alarm panel, telling it that someone has manually triggered the alarm.
So those are the things that initiate the alarm. But what happens next? How do people on the ship actually know there's a fire?
That's where the indicating devices come in. They are the things that actually make noise or flashlights to alert people. On the audible side, you have all sorts of things: sirens, bells, buzzers, horns, even voice announcements over the PA system. Some of those announcements are pre-recorded, telling people to evacuate, while others might be live instructions from the bridge or the engine control room. These alarms are usually both inside and outside the ship, so everyone knows what's going on. And on the visual side, there are usually flashing lights or strobes. Those are good for people who might not be able to hear an alarm, maybe because of a hearing impairment or because there's just too much noise in the area.
It's like a multisensory experience, no mistaking that there's a fire. And those systems need to be powered, right? What's the usual setup?
Most fire detection and alarm systems run on 24 volts DC. They get their power from the ship's main electrical system and the emergency switchboard. And to make sure they keep working even if there's a power failure, they usually have a backup battery system. That kicks in automatically if the main power goes out, keeping the alarms and detectors running for a while, enough time to handle the situation.
There is a whole section on the specs of a smoke detector that seemed pretty technical. What are some of the key things to look for in those specs?
Those specifications are important because they tell you everything about how that detector performs. Things like how often it checks for smoke, how much voltage it needs to work, the type of wiring it uses, how it handles a power surge, how much current it uses, how bright its LED indicator is, how long it takes to start up, how much of a load it puts on the fire alarm panel, even things like the temperature and humidity it can handle, how well it's protected from dust and water, its size, weight, and what materials it's made of. It's about making sure the detector is compatible with the system and can work reliably under all sorts of conditions. Remember, you're relying on these things to work when you really need them.
And what about the different types of fire detection and alarm systems that are out there? Are they all the same?
Not at all. They have conventional systems and addressable systems.
So what's the difference?
In a conventional system, the detectors and call points are all wired into groups or zones. So when a detector goes off, it tells the main panel which zone it's in, and that triggers the alarm first.